So let us now show that our greedy strategy for knapsack is in fact optimal. So remember that we have sorted our bags by unit cost, right? So we can assume that our bags are in order such that P1 by W1 is bigger than P2 by W2, which is bigger than P3 by W3, and so on. And the smallest of the unit cost is the last bag in our section. So what we had done in our optimum solution is that we moved in our greedy algorithm, right? We constructed x1, x2, and so on. So what we would do is we would try to pick up as much of the first bag as possible. In general, we would pick up all of the bag. Then we would pick up as much of x2 as possible. In general, we pick up all the bag, and so on until we reach some xj where we are not able to pick up the entire bag, right? So we will come to some xj where we will typically pick up a value which is smaller than 1 but bigger than 0. And now what's interesting is that after j we don't look at anything because our knapsack is full. So we have all zeros, right? So in general, the greedy solution will have the following picture. It will start with an entire sequence of ones, and it will end with an entire sequence of zeros, and there will be a position j at the end of the ones which is either 1 or something smaller than 1, corresponding to a fractional bag that we have selected to fill up the knapsack. So now the question is, how does one show optimality? How do we show that our greedy solution is optimal? So one of the standard techniques is to transform any optimal solution to the greedy one. And if we can achieve this transformation without changing the value, then since we started with an optimal value, the greedy solution must also be optimal. So this is exactly how we are going to do the proof here. Okay, so let y be some greedy solution. I mean, not some optimal solution. So this is some optimal solution. Okay, this is known to be optimal. We don't know how it was computed, but all we know is that the value of y in terms of the total quantity in the knapsack given by these fractions is optimal. You cannot do better than this. And what we have in our case is that we have a greedy solution which has possibly a different set of fractions x1 to xn, okay, and we have to argue that the two have the same value. Given that y is optimal, we have to show that x is also optimal. And what we know about the x's is that there is this xj, as we have just observed, such that from here to x1 to xj minus 1 we have 1, xj plus 1 to n we have 0, and this value is between 0 and 1. Okay? So the important thing to notice here is that the xi's were actually chosen in this sequence. We first did x1, then x2, and so on, because that was the greedy strategy. We have no idea how the y's were actually computed. We only know that y is optimal, but we can certainly assume that however y has been computed, it is reported in the same way as x. That is, y1 and x1 correspond to the same bag, y2 and x2 correspond to the same bag, and so on. So we are not assuming that y actually is constructed in the order 1 to n, but we are just assuming that it is reported in the order 1 to n. So the interesting case, of course, is when y is not equal to x. If y is equal to x, we have nothing to prove because y is optimal, so x is also optimal. So in this case, x and y differ. So let k be the smallest index where they differ. Okay? The smallest index such that yk is not equal to xk. There must be at least one such position, otherwise they will be equal. Now the claim is that in fact yk must be strictly smaller than xk. And this we can do by trying to figure out where this position k lies. So remember that x has this particular structure. So we have this point xj, and before xj we know that x is all ones. So here we have all ones, and here we have all zeros, and here we have something which is in the range 0 to 1. Right? So now we look at where k lies. So the first possibility is that k lies here. So here we know that each xi is actually equal to 1. So now if yk is not equal to xk, it must be different from 1. Now it cannot be bigger than 1 because the fractions have to lie between 0 and 1. So this implies that yk is in fact less than 1, which implies of course that yk is less than xk. So if xk and yk lie in the range 1 to j minus 1, we certainly have that yk is smaller than xk. Now at this point, supposing k is here, now we know that we cannot get more than xj without exceeding our knapsack capacity. The reason that the greedy solution put only xj is because it couldn't put any more. The knapsack became full. So xj is the maximum here. So now if yj is greater than xj, if it's not equal, it must be bigger or smaller. If yj is greater than xj, then we have something which is infeasible, because it means that the j solution has as much as the x solution. I mean, the y solution has as much as the x solution from 1 to j minus 1, and then it has tried to take even more than what the x solution did. But the x took the maximum allowed, and therefore y could not choose more. So therefore, this is not possible, right? So therefore, we have again that yj must be less than xj. And the last case, which actually cannot arise, is what happens if k is in the range j plus 1 to n. Now here, x is 0 because we have already filled up the knapsack. Now we are assuming that up to this point, up to j or little later, y and x agree. So y has also filled up the knapsack. So if y has also filled up the knapsack, then y must necessarily be 0 here, otherwise it will be infeasible. So here it is actually impossible. It's not possible for k to be in this range. So what we have shown is that the first position where y and x disagree has the property that the y coordinate is actually strictly smaller than the x coordinate at that position. So remember that our goal is to transform y into x. Okay, so now we have found the first position where x and y disagree, and we have that yk is less than xk. So what we will do is we will increase yk to be the same as xk. Now what has happened now is that the total quantity in y has gone up because you have increased it, and so now you will reduce yk plus 1 up to yn to restore feasibility. Because you have to drop something, right? So you have to reduce something in order to compensate for the fact that you've increased yk. Now you know that before that everything was the same as x. So there must be something that the missing part, the part that is missing in yk must be after k, and you just reduce it. Now it's not exactly important how you will reduce it, but you just reduce it in such a way that the total weight comes back to n. So what we have done in this process is that we have taken our solution y and we have transformed it into a new feasible solution, feasible in the sense that the knapsack is full, a new feasible solution which we can call z, okay, which in terms of coordinates is z1 up to zn. So what do we know about this z? Well, we know two things. We know that for every I up to k, okay, xi and zi agree, because zi is just the same as yi up to k minus 1, and yk was explicitly made to be the same as xk. So zi and xi agree up to k. And what happens after k? Well, after k we did this compensation, right? So we increased the weight by a certain amount. How much did we increase it by? Well, we increased it by wk times xk minus yk. This was the amount that we increased the weight in the kth component of y. And this was compensated by reducing the weight in the other components. So the weight in each of the other components is the sum of all the components from k plus 1 to n, and the difference between yi, which was the old weight, and zi, which is the new smaller weight, times wi. So wherever it decreases, the fraction that it decreased is given by wi into yi minus zi. If you add up this whole thing from k plus 1 to n, this must equal the amount that you added at the kth coordinate. So the proof hinges on the following claim, which we will establish, that z has the same value as y. So what we are going to show next is that z has the same value as y. Now suppose we assume this. So suppose this is true. Okay, then we know that z differs from x one more position to the right. Okay, so in some sense the number of coordinates which agree on z and x is one more at least the number of coordinates which agree in z and y. Now if z is not equal to x, we can repeat this argument for the first position where z and x differ, and we will get some new thing z prime. Now z prime in turn will again agree with x in one more position to the right than z did. So at each step we go from z to z prime and so on. We will produce new solutions which agree with x in one more coordinate. And at the same time, each of these transformations, if the claim is correct, preserves the value. So we start with the optimum value y, the same value is preserved in z, the same value is preserved in z prime, and so on. So ultimately, we will come to a final value z tilde where we have exhausted all the coordinates and we actually have a new solution which is exactly the same as our greedy solution. And since this is now an optimum value by induction, that is, we started with an optimum thing, at every step we preserved the optimality, and z tilde is optimal, and therefore this means that this is optimal, and so this is also optimal. Okay? So this is a typical greedy correctness proof. We start with any optimal solution and show that we can step by step transform it to the solution that the greedy algorithm produces, and therefore the greedy algorithm is also an optimal solution. So what remains is to show that z has the same value as y. So how do we show that z has the same value as y? Well, let's start with the expression for the value of z, which is just the summation of pi times zi from I equal to 1 to n, right? We just take that fraction of each profit that is reported in the zi's. Now how did we get here? We started with the solution y, which had value summation I equal to 1 to n of pi times yi, and then we added to this the quantity xk minus yk, because we increased xk to yk, and this produced a new profit of xk minus yk times pk, right? So this is the first step. We added this, and just for convenience I'm going to actually write this pk in a roundabout way as wk times pk upon wk. Okay, so the wk cancels, so actually we just have pk, but this will be useful. And now we did one more thing, which was we reduced the quantities in k plus 1 to n in some way. I don't know exactly how it has reduced, but I know that for I equal to k plus 1 to n, I have reduced the amount yi minus zi times pi, right? So these things have been reduced, and once again I'm going to write pi in this roundabout way as wi into pi by wi, right? So this is how I got the z's from the y's. The value of the z's is the value of the y's plus the quantity added at k minus the quantity I subtracted beyond k. Now the crucial observation is that we have pk by wk is bigger than all the pk by, because this is the unit cost at k and this is the unit cost to the right of k, and the unit costs are arranged in decreasing order. So the unit cost at k is bigger than the unit cost to the right, and so if I replace pi wi by pk by wk everywhere, I will get a larger amount subtracted, right? And since I have a larger amount subtracted, I claim that if I just replace each pi by wi by the fixed value pk by wk, I can write this as the following. I can say this is greater than or equal to the summation of 1 to n pi yi plus, okay, and now I pull out this pk by wk as a common thing everywhere. I say it is this into wk times xk minus yk minus the summation of wi times yi minus zi, I going from k plus 1 to n, right? So I can do this by, so all I've done is I've replaced the pi by wi by pk by wk and argued that this is going to be a larger subtraction now, so this becomes a greater than, and this is a common term. Now the crucial thing is what is inside this thing. I have wk into xk minus yk and I have the summation, and if you recall, this was exactly what we showed earlier as being the definition. The definition was that we reduced the later terms to compensate for this. So these are actually two equal terms, and so this simplifies to 0. This is equal to this. Wk into xk minus yk is equal to the summation. So this entire term now disappears. So therefore we have that the summation of the zi into pi is greater than or equal to summation to y into a. But it cannot be greater than, right? Because this is actually an optimum solution. The z cannot be more than y. So therefore, this must actually be equal, right? So this is how we show that z has the same value as y. So each transformation preserves the optimum value. And by repeatedly transforming our problem, we arrive at an optimal solution which is exactly equal to our greedy solution. And therefore, our greedy algorithm produces an optimal solution. Right? So to summarize, we said that knapsack with fractional weights, okay, has a greedy solution. Our greedy strategy is to choose by decreasing unit cost. So you start with the one with the highest unit cost and so on. And we showed a proof that any optimal solution can be transformed to match the greedy solution. Okay, and this is why the greedy solution is in fact optimal. So this completes the discussion about knapsack.